Good morning or good afternoon or good evening, depends on where are you located. Introducing myself, my name is Dr. Islam Mantawi, an assistant professor at Henry M. Rowan College of Engineering at Rowan University, who will be moderating today's research seminar as part of education and workforce development and technology transfer activities at IBT ABC-UTC. IBT ABC-UTC is University Transportation Center funded by USDOT to advance the frontiers of bridge engineering, bridge technologies, and ABC. Today's presentation is exploring fiber-reinforced polymers concrete for accelerated bridge construction. The seminar is presented by Dr. Travis Thonstad, an assistant professor at Civil and Environmental Engineering Department at University of Washington in Seattle, and Carolyn Donohoe, structure associate at Moffatt and Nichol. I would like also to introduce and thank Paul Lyles, who will moderate the Q&A session. Paul is the former Georgia DOT state bridge engineer. Along with Paul, Dr. Jamal Al-Qaisi from FHWA. I would also like to thank Dr. Atarad Azizi Namini, the director of IBT ABC-UTC, and Kathy Crow, IBT ABC-UTC Director of Technology Transfer, who helped organizing this seminar. Finally, I would also like to thank Dr. Ankita Arvind and Dr. Ali Javed for coordinating the web room and the Q&A. Now I will turn the presentation to Dr. Thonstad and Carolyn.
Thank you for that, Islam. Appreciate the introduction. So today we're going to be talking about fiber-reinforced polymer concrete and its use in ABC applications. And the objective of the presentation for me today, I think, is to give you some understanding of this new material, if you're not familiar with it, talk about some of its unique properties, and then present the results of some testing that we've done to try and characterize it and to see if there are uses for it as a closure pour material for ABC projects. And for this crowd and the ABC-UTC, the advantages of precast superstructural elements are numerous and to folks here are known. So we have reduced traffic impacts, improved worker safety, and component quality. So all good things. Let me see if I can get this. There we go. And here's an example of a project that is using precast deck panels. And this is one that is out of FHWA publication. You can see the panels there. You can also see the joints in between the panels where they're going to place UHPC. And that's the same place where you would have this potentially alternative material. And it's not just for deck panels. This could also be an application where you have deck girders. So you have two deck girders, you have a closure joint in between those deck girders as well. And the width of that closure joint is largely determined by the tension and bond strength of the closure joint material. So you can see you have those protruding reinforcement from one element to the other, and those need to be spliced in our joint. And that's going to happen through a non-contact lap splice. And UHPC is a perfectly good solution for this, and it's a preferred solution presently. The reason for it is, of course, its high tension and bond strength. It allows you to have very small closure joints as opposed to traditional cementitious concrete. And so you can see a typical geometry for that joint here. You have a minimum cover of about 3 bar diameters. You have an embedment length of 8 bar diameters, a splice length of 6 bar diameters. If you put all those things together for a bar with yield stress of less than 75 KSI, you get about 10 bar diameters in terms of that minimum joint distance. this is for UHPC with greater than 14 KSI compressive strength and fiber content larger than 2%. And for many applications, UHPC would be the logical choice. One of the challenges with UHPC and all cementitious materials is that the rate at which they gain strength is controlled by the hydration of that cementitious binder. And so for an application where you need strength quickly, very quickly, in a matter of hours, there may be alternative joint materials that would be worth exploring. And one option for that is polymer concrete. The advantages is that you get a rapid strength gain, about a 4-hour traffic return is possible, so perfect for an overnight closure window. You have a high tensile strength comparable to UHPC, up to about 2 KSI, and you get excellent bond to concrete and reinforcement. And that's because essentially this stuff is glue, right? Where it's a polymer, it's going to have a good bond to concrete and reinforcement. Some of the challenges with polymer concrete that we'll explore today is that polymer concretes, because they have a polymer, they have temperature-dependent properties. And characterizing those temperature-dependent properties is important. And thinking about those properties over the range of service temperatures is a design consideration that may not be as familiar as it would be with a UHPC or cementitious concrete. It's a fairly new material, and its use as a structural material is very new, so that there's a lack of design guidance. And because this is a polymer, you have to worry about creep. And creep was out of the scope of our present study, but it's certainly an important aspect that requires further thought. Why polymer concretes? Why were we investigating them? Well, polymer concrete overlays have an established history of use in our transportation infrastructure. Overall, that performed well, and I'm showing you an example here of a test patch that was done in Spokane, Washington after 6 years. The reason I say it was a trial is because they've used a couple of different strategies to fill in those wheel ruts, and so that's why you see a couple of different strategies in this particular patch of highway. We have polymer concrete overlays in Washington State that are in very good condition after 30 years. So contractors are used to dealing with this stuff. We've used it in the past, and it's performed well overall as an overlay and a repair material. And so now we start thinking about, can we use it as a structural material? Can we use it in these types of applications for ABC, where we need to connect elements together quickly? And there's been some testing done. So this particular set of tests were done by my colleague Islam Mantawi while he was at the University of New Mexico. And he was looking at splicing bars in a flexural beam there. You can see the picture there on the right. And the plot here is showing the maximum bar strain at the peak flexural strength. And you can see that if the bars were lapped for 6 bar diameters or larger, you got significant yielding of the bars. So 6 bar diameters in terms of a lap splice length is comparable with what we would see with UHPC. So that was promising in terms of the results. We also have some testing done as part of the ABC-UTC at the University of Nevada, Reno. So this was some testing done by Muhammad Mustafa, and they looked at some precast deck panels and a closure pour between those two. And they compared UHPC and PMMA, or polymethyl methacrylate polymer concrete. And they had a simple setup here where they had we had 2 precast deck panels, lines of support, and they had a loading point there at the midspan. And to compare those 2 curves, I'm showing you the load in the actuator versus the vertical displacement at either the midpoint or a point adjacent to the midpoint. And the green curve in this case is the polymer concrete, the PMMA concrete, and the blue curve is UHPC. And so you can see the test method here. They took this assembly up to a service level several times, cycled it there, and then pushed it until they reached the peak strength. And in the red lines there show you the AASHTO LRFD service and ultimate load levels. So both specimens achieved greater than the ultimate load level based on AASHTO LRFD. The response was similar between the two panels. You can see the dashed and dotted lines are those points adjacent to the midpoint, and the solid lines are the midpoint displacements. So overall, behavior very similar. Did see a slight reduction in strength, but in terms of damage patterns and everything else, the two were quite similar. So both of those tests show some promising results for the use of polymer concrete as a closure pore material. They were both done at laboratory temperature. And one of the things that's important to understand about polymer concretes is that the mechanical properties depend on both time and temperature. So we're used to time with our cementitious concrete. The only difference is, as you can see with the legend here, we're talking about a matter of hours versus a matter of days and weeks. And what I'm showing in both curves is the stress-strain behavior of a concrete cylinder in a test machine. On the left, you can see the rapid development in strength and stiffness. On the right, you can see the dependence of temperature. At a low temperature, the material is stiffer and stronger. It actually exceeded the test machine capacity in this case, which is why those lines suddenly end. As you increase the temperature up to, in this case, 110 degrees Fahrenheit, you can see that the compressive stress strain behavior becomes much more flexible and loses some capacity. And that just has to do with the nature of polymer concretes and their chemistry. And the chemistry there is what leads us into an understanding that not only do all polymer concretes have a temperature dependence, depending on which polymer you use, you get a different relationship. And so there's a lot of chemistries out there that have different dependencies on temperature. And so it's important to understand that for each one and whatever product that you end up using. So in this case, I'm showing a plot of flexural strength. This is just a 4-point bend test. And I'm showing you results for both an epoxy mortar and for polyester mortar. And because I'm in Western Washington, I gave you the range of service temperatures in Western Washington. But you can see that over that range, the difference in material properties for the epoxy mortar is quite different than the difference in material properties for the polyester. And so characterizing that is critical anytime we have a new material that comes to market. Also similar to cementitious concrete, the rate of strength development is affected by curing temperature. And so what I'm showing you here is the compressive strength versus time for cylinders that were cured and tested at 3 different temperatures, at 32 degrees Fahrenheit all the way up to 110. And what you see is that as the curing temperature increases, the rate of strength development becomes quite rapid. You get 100% of the strength in about 2 hours. And then it levels off here at a lower strength than, of course, the colder temperature values. As you cure at a lower temperature, the rate of strength development goes from about 2 hours to maybe 2 days. And one of the interesting things about polymer concrete is that the rate of strength development can also be affected by the by the addition of an accelerator. And so there's some tuning that you can do depending on the temperature at placement, which can help you normalize these curves to be something closer to what you'd expect at room temperature. So now, anytime I talk about polymer concrete, people ask me, so what are the material properties of this and how do they compare to UHPC, which is what we've been using for this particular application. So I'm showing you a comparison here of 3 commercially available polymer concretes and comparing them to a UHPC. And what you can see right away is that the compression strength is lower. It's closer to that of conventional concrete. The modulus is also lower, and this is now lower than conventional concrete, and that has to do with the different binders. What's promising and why we explored this material as a closure joint material is the tension strength and development length are both quite similar. So you can see the tension strength for UHPC and for the polymer concretes is greater than 1 KSI, and the development length is on the order of 6 to 8 bar diameters. The material I'm going to be talking about today, and Carolyn will talk about her research, is HCSC. And what is HCSC? It's hybrid composite. The acronym is Hybrid Composite Synthetic Concrete. It consists of graded silica aggregates, basalt chopped fibers. These are microfibers, which help with some of the microstructural properties of the material, and a urethane vinyl ester hybrid copolymer binder, which is a mouthful, but it gives you this nice gray color. You can see that it looks very similar to what you would see in a concrete. To allow this material, or to aid it rather, in bonding with concrete and steel substrates, a high molecular weight methacrylate primer is used. And this really helps to bond the two materials together and prevent the binder from leaking into the existing concrete, so that you get a good hydration, or not hydration, excuse me, you get a good cross-linking between the binder and the aggregate. So what does this look like in terms of the chemistry? So the binder comes pre-packaged with your resin copolymers and your cross-linking agent. That's a convenient way to package this material because you can mix it in different components on site. So you're not to that binder, you add an initiator, in this case a methyl ethyl ketone peroxide. That's what starts the cross-linking reaction. You can also add an accelerator at different dosages to control the speed of that cross-linking reaction. And at the end of the day, you have a cross-linked copolymer, which is binding the aggregate and fibers together. One of the reasons that this material is nice is that for the contractor, it's easy. It's pretty straightforward to put this stuff together. You add the initiator and accelerator to the binder. You mix it with a squirrel cage mixer, in this case, for about 30 seconds. You add that and the aggregate to a drum mixer, mix it for a minute or two, and then cast your specimens and finish. And this works well for the laboratory, and it can work for small volumes, potentially like these closure pours. If you need to make a lot of this stuff, then you can use volumetric mix trucks. And this is an example from that same project in Spokane, where they're using polymer concrete to fill in some wheel ruts. And so this project that we're talking about today had 3 objectives. The first one was to characterize the mechanical properties of fiber reinforced polymer concrete at multiple temperatures and ages, to characterize the splice performance of deformed bars embedded in fiber reinforced polymer concrete materials at multiple temperatures. And the third was to develop some preliminary design recommendations for the use of FRPC in closure joints for ABC applications. And so now the first thing I'm going to turn this over to Carolyn so that she can describe her research looking at the mechanical properties.
Thanks, Travis. Yeah, so like Travis said, the first phase of the research was to look at the mechanical properties. Some of the purpose of that was to sort of just get a better understanding, that hands-on understanding of how can we work with this material, how can we handle it in a small lab setting, and then based on that knowledge, use that to develop the other phases of research. So we primarily did 3 tests for mechanical properties. Your 3 standard ones: compression, 4-point bending flexure, and bond. Something that we did between all of our tests, mechanical and non-contact splice testing, was we looked at the 7-day compressive strength from every batch. And those were always cured and tested at approximately room temperature. From that, we were able to see that we not only get consistent results between batches, but that we see that compressive strength of about 92 to 9400 psi. Like Travis had mentioned before, the influence of accelerator gives you a trade-off between working time and strength gain. So on the low end, you have about 1% accelerator, that's by volume initiator. The high end of a working time that you could see is about 20 minutes, so still something pretty rapid. And it takes about 4 hours to get you 70% of your 7-day strength. On the opposite end is an 8%. It brings your working time down to 7 minutes, but gets you that 70% strength in 2 hours. So really you're trading off your working time with your strength gain, and that can be tailored depending on what your conditions are at the time of casting or pouring. For our tests, we used 3%, so around 15 minutes of working time, and like you'll see coming up, about 4 hours to reach that 70% marker. Looking at the strength gain over time, diving a little bit more into it, for all of these specimens, we cured and tested them at room temperature, so about 70-75 degrees Fahrenheit. These 4 plots have their strength values, so compressive strength, modulus of rupture, bond strength, and elastic modulus on the y-axis, and then here in hours time on the x-axis. We tested these pretty frequently at the early stages of curing to see that rapid rise in strength, and then like we had seen before, it sort of levels off as we approach 7 days. Something to note from these plots is the comparison to UHPC. This is a non-proprietary UHPC strength. That's that black dashed line that you see usually at the top of the plot, sort of seeing how each of these markers of polymer concrete compares to that of UHPC. Awesome. So here we normalize all of these plots. The 1.0 normalized strength is that of 7 days. And so again, we're seeing with that 3% accelerator cast and cured at room temperature, it takes about 4 hours to reach 70% of the final strength. The next variable that we looked at was testing temperature. I really want to highlight that this is the testing temperature, not necessarily the curing temperature. So these were cured for 7 days at room temperature and then conditioned for at least 16 hours at the testing temperature to ensure that the entirety of the specimen had reached that test temperature. This is something that would maybe mimic more in the field of something that's poured during a quote-unquote usual temperature, and then you're seeing these results at the extreme heat of summer or the extreme cold of winter, but one where they were placed at a more average temperature. Again, compressive strength, modulus of rupture, bond strength, and elastic modulus. We're seeing a similar trend here, similar to what you would see with other polymer concretes, is that at low temperatures, you're seeing higher strengths, and at high temperatures, you're seeing lower strengths. We used 4 testing temperatures here, one around 0, a little bit warmer than 0 Fahrenheit, that is, one around freezing, so about 32 to 40 degrees, one at room temperature, and then one around 110, 115. Again, we normalized these. In this case, our 1.0 is at room temperature. And again, we're seeing, hey, all of these properties are exhibiting similar behavior with temperature, so you're not having one that's significantly different than the rest. We said, hey, this looks vaguely linear. Can we plot this to a line, a linear regression? And looking at compressive strength, modulus of rupture, and bond strength, we were able to, just in a generic summary, you get a 25% change in strength for every 40 degrees Fahrenheit. So just some numbers to throw out there when you're thinking about, hey, would this be good for the geographic area in which we could apply this? So the next phase of research was to look at the splice performance. We utilized the results from the mechanical properties testing to create a good bracketing for all of our variables, as well as giving us a little bit of heads up as to some of the results that we could see. We utilize non-contact splice tests. This is similar to curb testing, which was done on UHPC at the FHWA. The specimen that they used is shown in the lower left-hand corner on your screen. We adapted that a bit, both in how it was tested and what the specimens looked like, to be able to test at different temperatures as well as to fit in the testing in the lab that we had at the University of Washington. So you can sort of see how this non-contact splice test would mimic that of a closure pore. That's the figure on the right-hand side. So we're providing tension between the closure pore and your prefabricated element, and that tension being applied to the reinforcement. At the very beginning of this phase, we did a small scoping study to investigate the influence of primer. So that would be primer applied to the cold joint as well as the reinforcement between a cementitious concrete and a polymer concrete. The brief summary of that is it makes a small difference, but for the rest of our research, we followed the guidelines of the material and the manufacturer, which meant that we did apply primer to all of our specimen. For the main chunk of this non-contact splice testing, we used a fractional factorial design. Pretty much that means you have repeated center points within each of your batches that are repeated to ensure that you have consistency between each batch. And then you're modifying each of your variables to create your axial and factorial points. This all sounds very fancy. It just gives you the ability to statistically analyze it in a way that's easy and provides good results. So the 4 variables that we looked at for these non-contact splice tests were temperature, splice length, side cover, and bar size. When I say bar size, I'm referring to the epoxy-coated bar, so the green one in the figure there. And then we followed a similar temperature range, going a little bit hotter than we did for the mechanical properties. So we ranged from 5 degrees Fahrenheit on the low end to 145 on the high end. And just to break down what this specimen looked like a little bit more, we had 2 number 8 bars, just a standard rebar, and that was embedded in 6 inches of cementitious concrete. And then those number 8s stuck into the HCSC. That's the gold section in that figure. And that's where the splice occurred between our epoxy bar and our standard number 8s within that HCSC. Here's a little bit busy of a slide, but it breaks down each specimen that we cast and tested. So overall, we tested 40 specimens. So that batch 0, that gray block, is the investigation of the use of primer. And then the blue, green, and orange are block or batches 1, 2, and 3, which were the main component of this test. Not to go too much into it, pretty much you can see that those pluses and minuses are how far from the center point we went for each point, as well as the observed failure and bar stress, and Travis will go into that in a little bit. To give you a picture of what these look like in real life, not just a figure, the top left picture is in the middle of the creation of this specimen. So those boxes were what was used as formwork. The current stage of the specimen here, we have the number 8s embedded in the cementitious concrete. That's the existing concrete block that you see there. And then the epoxy bar is put in that formwork, and you can see the splice length for those particular specimen. Like I mentioned, that use of primer that was applied to the cold joint between the cementitious concrete and the HCSC, that polymer concrete, as well as being applied to the anchor bars and the test bar. For the surface, that cold joint, we had an exposed aggregate surface. So we applied a retarder to the cementitious concrete and then brushed and blew it off. Once fully cast, cured, and brought to temperature, you can see the testing rig and the setup on the right-hand side. So we have the cementitious concrete on the bottom with those anchor bars. Those threaded bars are then tied into that steel plate. The HCSC is on the upper portion, so you can see that similarity in color and texture. And the epoxy-coated bar is grabbed in the chucks of the testing machine, and that whole thing is put in tension. The main thing that we collected, that main data point, is the displacement of the epoxy bar with comparison to the top surface of the polymer concrete. We also recorded the load from the machine itself. There is a thermocouple embedded in the specimen that allowed us to track the temperature not only while testing, but also while curing. I'm going to pass it back over to Travis, and he's going to go a bit into the experimental results.
Okay, thank you, Carolyn. I really appreciate that. So now I want to talk to you about the experimental results. And so I just wanted to say briefly that this test specimen is meant to represent sort of a worst case. So you'd imagine that in a structural context, you'd have a lot of restraint provided by adjacent elements. And so this is going to really give us a conservative estimate of the bond strength that you'd expect from a non-contact splice. Like Carolyn said, we used the results from our material properties testing to develop the experimental matrix, expecting that we would get a range of failure modes. And so that's what you see here. So the majority of specimens failed through splitting, as you might expect. You can see what one of those failures looks like. That safety restraint that Carolyn was showing you, which went around the concrete block, was just meant to help restrain this crack and make sure that it didn't go all the way through. And that was really just to protect the instruments. So it was only snug tight. It wasn't tightened. It wasn't meant to confine anything. It was mainly just there to arrest this crack before it reached the bottom and split the specimen in half. You can also see bar fracture and pullout, and those are going to be at the extreme ends of our design space. And I'll explain a little bit more about those points in a moment. So one of the strengths about this design, this experimental design, is that you are able to look at these replicate specimens and determine the batch-to-batch variability. And the hope is that that's small, and then you can use the entirety of the results without having to do any normalization. And that's what you see here. As Carolyn showed in the bar chart at the beginning, this stuff has very repeatable properties, and we saw that again with these results. So coefficient of variation of about 2.7%. You can see the curves on the left, stress versus front end displacement measured there, and very, very consistent. So that gave us confidence that we would be able to combine the results from all three batches of material into one statistical analysis. Now, in doing this sort of study, you have a lot of points and you change a lot of variables, and you're not necessarily looking at one factor at a time sort of excursions. And so it is nice as well to look at the influence of an individual variable and look at some pictures. And so what I'm showing you here is the influence of three parameters: side cover, temperature, and the splice length on the behavior of these test specimens. And for reference, we've shown in the dashed black line the response of a number 5 epoxy-coated rebar. And how we calculated that value is we took the stress strain curve that we measured as part of the test series and multiplied it by the free length between the top of the specimen of the HCSC and the location where we measured the front end displacement. And so if you see a difference between one of these curves and the black dashed line, you would interpret that to be slip. And so you can see that for the most part, you're seeing very little slip for many of these curves. And you can also start to see the slight differences in behavior at the extreme ends of our design space. It's hard to see, but for a side cover of 0.75 inches, we saw the blue curve come up and it stops about here. And so then we saw a splitting failure there. We also have temperature up here. You can see the difference between 5 degrees Fahrenheit and 145 degrees Fahrenheit. The blue curve follows the stress strain curve of the reinforcement quite closely, meaning we didn't see much slip at all in that test specimen. Whereas at 145 degrees, you're seeing quite a bit of slip in the test specimen, and you see pullout that occurring in that case. The last one is looking at splice length. Again, we have 3 different values here. We have the extreme ends of our design space, so a very short splice length of 1.25 inches, the blue curve here, and that is showing you that we have a pull-out failure at a lower than the yield stress. And then we have the other end where we have a long splice, and you can see that also tracks very nicely with the stress strain curve for just the rebar, the reference curve. And so we're able to take all of this data now and start to analyze it and start to come up with some conclusions. And so one of the first conclusions, one of the things we wanted to look at was how does this compare to non-proprietary UHPC? And so that's what we're showing you here. So we have the peak bar stress on the y-axis, we have the normalized splice length on the x-axis, and I'm showing you the yield and ultimate stress of the reinforcement in our test case. And what you can see is, especially for the lower temperatures, which are shown by the darker blue color here, we're tracking very well with the non-proprietary UHPC. As temperature increases, as the dots become more lighter green or yellow, you can see the yellow dot all the way down here, up at 145 degrees Fahrenheit, you get a change in the strength, and you see a slight reduction clearly indicated up here and also in this region. And that's what we'd expect, right? We know that the temperature is going to reduce the bond strength slightly. Overall, though, comparable to the non-proprietary UHPC. So now I'm going to delve a little bit into statistics here, and what we did with this design, experimental design, allows you to go through and look at a statistical analysis and quantify some uncertainty. And so I'm going to show you some plots from the resulting numerical model. So we're showing you the mean surface, which has its own limitations, but at least give you a sense for the way the space works. We took this data, fitted a quadratic model, which you can see what that might look like here. There's an error term, there's an interaction term, so do the variables interact with one another? You can have a squared term, so you can have some sort of plateau, and linear terms as well. And what the analysis allows you to do is slowly eliminate non-statistically significant terms. So the question is, are these terms good predictors for the response? And it turns out that not all of them are. And so you get some understanding of what's going on here. So right away at the beginning, Carolyn said that we did a scoping study to see what the influence of primer was. And so this is the results out of that scoping study. Because it was a fractional factorial design, you only get the main effects, which is the effects of the variables by themselves. And this was all done for a single bar size. So we didn't investigate bar size with this set of tests. What you can see is what you would expect. So as splice increased from left to right, you get an increase in the bar stress before failure. If you increase cover, you also get an increase. And with temperature, as you increase temperature, you get a decrease in strength. So the trends all make sense, and that's good to have. The next thing is comparing tests without primer to tests with primer. You can see that there's a shift in the average stress, and that shift is about 10%. You can also see that it shifts the stress to be above the yield stress. And so those were all reasons why, when we went to the next phase of testing, that we decided that it made sense to use the primer. And again, this is probably just the biggest influence is just how the primer is helping bond to the reinforcement. But in an actual application, that primer is primarily there to help bond with the concrete. So while there might be applications that priming the concrete is more difficult, it seems worthwhile for some increase. Now we move on to the statistical analysis of this 30 specimen experiment. And I'm showing you here the final model, and I'm showing you the main effects, which is just the influence of one of the variables by itself, and also the interactions. And I'm just going to start with the main effects to just talk through this with you and try and explain what you're seeing here in these plots. So on the x-axis for this first plot, you see surface temperature. And what you're seeing is essentially as you go down in surface temperature, you eventually reach a point here where you plateau. So you're able to achieve some peak bar stress and no more. And really what that's saying is that as temperature decreases, eventually you break the bar. And so there should be, as you would expect, some plateau of mean bar stress as temperature decreases. The same thing is true over here when you look at splice length and side cover. At a certain point, if you have enough splice length or you have enough side cover, you might expect that you would be able to fracture the bar. And so that's why you see an increase, then plateauing to some peak value on the right side of these plots. Diameter is a slightly different story, and you see that as the diameter decreases, as the diameter increases, the mean bar stress increases. And that should be sort of an indicator that normalization might be necessary. And so that's what you really see in these interactions. So these interaction curves are telling you how one of the variables varies in response to the other variable. And so if there is an influence based on diameter, this is saying that the way that the surface changes with splice length varies on what diameter bar you have. And the way that this surface changes with side cover changes with the diameter of the bar. And that's great in terms of statistical analysis. As an engineer, you put your engineer hat on and you would say, well, wait a minute, I would normally normalize splice length and side cover to bar diameter. And what would that do? Well, what that would do is it would take this green curve, which is one diameter, a larger diameter, it would shift that to the left, and it would take this blue curve and shift that over to the right. And so if you normalize splice length by bar diameter, what you really see is that the green, the red, and the blue curve are essentially all part of the same curve, but just at different locations. So the interaction terms that you see here, the influence of diameter there, in this case, we're just showing and confirming that these lengths, that these variables, splice length and side cover, should be normalized by bar diameter. And that's what leads me to this plot, which I think summarizes all of the experimental testing that was done in a very succinct way, albeit requiring some explanation. So it's all here. We have our 3 different temperatures. So 40 degrees Fahrenheit is the top row of plots, 75 degrees Fahrenheit is the center row of plots, 110 degrees Fahrenheit is the bottom row. Bar size, we go from number 4 bars to number 5 bars to number 6 bars on the right. And then within each of these individual plots, we have the normalized splice length on the x-axis and the normalized cover on the y-axis. So we have all 4 of the variables that we investigated, and shown in each of the panes is a contour plot of the bar stress at failure. And as you increase the normalized splice length and as you increase the side cover, you see that you have a plateau which occurs in this upper right corner. In terms of variation versus temperature, you can see that the yellow dots get smaller and the blue circles get smaller as you go down. So that's just saying that as temperature increases, the bar stress decreases. That seems true as well. If you go from bar diameter now, you start seeing a lot less variation, which is exactly what we're talking about with this normalization. What I'm also showing in each of these plots is some white lines, which would tell you the UHPC recommendation. So they would recommend a cover, CB, in this case, greater than 3.5, and a splice length greater than 6. And so what we're really looking at in each of these plots is what's going on here in the red box. We're also showing contours called out for both 60 and 75 KSI, so you can see it. And so what we observed is that for the range, in the range of parameters that we investigated, if you look at this top right box, you see that we're achieving at least 60 KSI in all cases and 75 KSI in most cases, even up to 110 degrees Fahrenheit. And that is what gave us, that's what gave support to the idea that this could be a potential replacement one-to-one for UHPC in certain applications. And so now, to summarize everything, we're going to go through the design recommendations here. And so, in conclusion, the strength gain over time of polymer concretes and the fiber reinforced polymer concrete depends on curing temperature and can be tailored to specific needs by varying the amount of accelerator. In our case, we use 3%. The manufacturer recommends 8.3%, and that would be much. That would be for a field application where you're not trying to fuss with all these specimens. There's a trade-off between working time and rapid strength gain. That was that table that Carolyn showed you. The mechanical properties are significantly influenced by temperature, and that was that 25% change, either plus or minus, as you vary 40 degrees Fahrenheit. The primer had an influence on the bond strength, up to about 10% increase. We did not assess concrete to HCSC interface strength, and that's really what the primer helps with, and so that would be important to understand that as well. Splice strength increases with the larger splice length and larger cover, just like it would for any other cementitious concrete. The new unique feature here is that bar stress decreases with higher temperature, which is a new consideration for design. So preliminary design recommendations: that this initial testing supports direct replacement of UHPC with HCSC for in-service HCSC temperatures less than about 110 degrees Fahrenheit. Maybe that's 120 degrees Fahrenheit. Certainly when we got all the way up to 145 Fahrenheit, then we saw a significant reduction. And that's because, you know, at some point where you're going to get close to that transition glass temperature and things are going to become more rubbery. For higher temperatures, it's not to say that you couldn't use HCSC. It just means you need to think about increasing your splice length in order to accommodate those higher temperatures. And of course, when you're thinking about this material and its structural use, you really need to consider what is the temperature where the joint is in your structure, which is a different consideration than you might be used to. So in terms of outlook and future work, so HCSC is a promising alternative closure pore material. Again, we didn't look at creep, which would be another important consideration. Service and ultimate level joint testing would be needed, so we've done some of that at UNR for the PMMA concrete. It'd be helpful to do some more of that for HCSC and other polymer concretes. It'd be important to look at various test temperatures and repeated cycling at service levels. The influence of the time and rate dependent properties, so this is thinking about creep, and also the fact that the dynamic modulus for polymer concretes is quite a bit higher than the static modulus. And so that's something that is important to consider as well. It also, in addition to everything we talked about today, has some rate dependent properties as well. And I just wanted to point out that there's an ongoing PennDOT project that's being done by David Manti at Lafayette College, who is building some more of these precast deck panel specimens with HCSC closure pores. And so hopefully we'll get some more results from that shortly. With that, I'd like to have some acknowledgements. So certainly I'd like to thank the IBT ABC-UTC for their funding and for all the folks here that are helping support this webinar today. I'd like to thank Quick Bond Polymers for the in-kind material contribution that allowed us to do this work. Casey Rafter and Dan Uldall for all of their technical assistance and guidance throughout the project. And then our project's advisory panel, Anthony, Steve, and Dwayne, who provided a lot of insight and direction as we were approaching this test series. And with that, I'd like to say thank you, and I'm going to turn it back over to Islam.
Thank you, Travis. Interesting presentation. And now I will hand the presentation to Paul Isles to moderate the Q&A session.
Okay. Thank you, IM and Travis and Carolyn. Very, very interesting, real intriguing about using the real fast setup with it, your material. We do have some questions that came in beforehand, and we've got some questions that have come in afterwards, and we'll go ahead and get in them. The first questions I have here are just general questions, and the first one is, are these applications considered structural? That is, restoring the structural capacity of maybe existing bridge elements?
So I think that currently, the polymer concretes are used for overlays and non-structural applications. And the question, and I think what the change in the industry may be is using them as a structural overlay or as a structural component. I something like closure pores, full patch repairs or something like that. So yes, there is structural use of these materials. They're certainly, you can see from the compression stress strain curve, we know the modulus is lower. We know that the deformability is also greater, and so you could consider thinking and looking at how the strength would compare based on overlaying this and the initial stresses that are present plus what you'd get after the overlay. So there's certainly analysis to be done to see if you would get a strength gain for a particular application, and I think there are regions of the design space where that would make sense. In terms of what we're talking about here today, yes, the idea is you could use this as a structural material for closure pores, and it's important to understand the different behavior of polymer concretes versus cementitious concretes in order to do that.
Okay. The next one, this came in pre-webinar, was how does steel fiber reinforced concrete weather in heavy chloride environments?
And so I think that's one that's outside of the scope of our investigation. I think it's a great question, and certainly I thank whoever asked it, but unfortunately for us, it's not what we're investigating in this case.
Okay. Your basalt fibers, they hold up pretty well for salt?
Basalt fiber, so yeah, they're microfibers in this case too. So they're really there to help with the microstructural properties. But basalt itself, there's a history of use there. So I would suggest anybody who's interested to look at some of the existing literature on that.
Okay. Another question that was pre-webinar, would this be useful in deck continuity for live load applications over simple support structures?
I think the answer is yes. I think there's some interesting pieces there. I could go on and on about for lots of for minutes about that in terms of some of the unique ideas there for precast pre-stressed girders as well, and how some of this material might help some of those continuity connections. So I think that's one that the short answer is yes. I think that's an application for this material as well. And whoever asked the question, if they want to shoot me a message, I can expound at length on some of the other applications that might be quite interesting to look at.
Okay, I just want to tell everybody that we're going to have a UHPC link slab presentation at the monthly webinar in April, so be on the lookout for that. Anyway, the next question we have, this is also pre-webinar, is fiber reinforced concrete suitable for sprayed applications, such as use of gunite for concrete repair and rehabilitation projects? Your mix? I
think it's an interesting question, and we didn't think about this material for spray applications. That wasn't necessarily the focus of what we were looking at, but that would be something to consult with the manufacturers about, and to see if they have any experience or any recommendations for potential spray applications.
Okay. We did have our last research meeting, our last research presentation was on UHPC shotcrete. It was it was the presentation on that.
Absolutely. Yeah, no, I can see the benefit, and certainly, like I said, I think it would be, I don't want to say anything that I don't know enough about. So I think that would be something to
Okay.
check out with the manufacturers
Okay.
about.
Good enough. Another general question is it advisable to use this material in constructing essential category buildings, such as hospitals, maybe?
Yeah, and so I think just like so many other different types of materials, there is, this material, thinking about costing and things like that is similar to UHPC. And so you're not probably going to want to use this everywhere. And so you really want to find those locations within the structure or within the bridge that make the most sense to use it. And so that's why I think ABC is a really great application for this material, because you're using its unique properties in locations where it can help you, and that's the rapid strength gain, the high bond strength, the high tensile strength. And so if you can find locations within the structure where that makes sense, then I think it's a wonderful alternative for that type of application. For structures and for high loads, the other thing to consider for all polymer concretes, not just HCSC or PMMA that I described today, there is the issue of long-term loading and what that does. And certainly in buildings, especially for polymer concrete, there's the issue of fire. And so that's something that you need to consider when you're thinking about using any polymer concrete for those critical structures. And ACI has a polymer concrete document that describes some of those, some additional uses of polymer concrete for both structural and non-structural applications in buildings. And I can certainly put that in the Q&A chat so that folks can go and look at that.
Okay. Let's look at some questions regarding your research, specific questions. The first one, this came in pre-webinar. What was the amount of fiber in the mix, and what is the concrete tensile strength of the material?
And so I think the tensile strength was, we talked about that in the presentation. So it's about 1.5 KSI in direct tension, and that's according to the manufacturer's specifications. And you saw the flexural strengths, and of course the influence of temperature on those, which is important. In terms of the fibers, I think probably there was pre-webinar, there might have been thoughts that these were macro fibers, and so those macro fibers would have some reinforcing properties. And I think the thing to remember for these fibers in particular is that these are microfibers, and they're really there to help with things like the coefficient of thermal expansion and the durability and things like that. So in terms of the volume added, that's all done by the manufacturer. It comes in a pre-blended bags in this case. And so there's not a real need to adjust that in terms of the volume. If you want the specific volume for just knowing some sort of curiosity or because you have some specifications, that would be a good question for the manufacturer.
Okay. The next one was came in pre-webinar was how do you manage or handle the fiber lumps in the concrete during mixing?
And I think that one too probably goes back to the idea of having macro fibers, something like steel fibers or macrosynthetic fibers, which would exhibit those clumping tendencies. For this case, the volume of fibers being at where it is, and with having the manufacturer sort of optimize that quantity, we didn't see any issues with fiber clumping. I mean, these are microfibers. And so, the good dispersion, we didn't really see any sort of big balls form with this stuff. It's a very flowable material, and you can tune that by how much binder you use. So the percent binder by weight aggregate, and it mixes well, and so you don't necessarily tend to see clumping like you would if you're trying to add a high volume of macrosynthetic fibers or steel fibers.
Okay, here's one that came in during the webinar, and this was very, very early on, but it said, with challenges listed with temperature dependence, do you have data on the high temperature limit range?
Yeah, I think that's a very important question. Yes, yeah. And so for us, we were certainly looking at service temperatures. And so we were sort of considering things lower than 120, 110, somewhere in that range. We did test one point out at 145 Fahrenheit, and you saw that was a significant reduction in strength there. And the other thing to consider is just like I said at the introduction, is that every particular binder chemistry has a different temperature dependence, and so with epoxies, for embedding rods and things like that, or dowels, those have been designed to have a transition glass temperature much higher than some other polymers, and so it really depends on binder chemistry. We did not specifically set out to investigate where that portion of the curve was, but focused mainly on applications with a service temperature less than 120 Fahrenheit. But it would be a good thing to consider if your in-service temperature you expected to be much higher than that.
Okay.
Which depends on many factors, obviously. So it's not an easy question to answer, but.
Okay, no, that's fine. Another question that came in during the webinar, it said you had the temperature, you had a 25% change, and they want to know if that was up or down the curve. They felt it made a difference.
Absolutely, yeah. So it's what we found with the testing was that relationship in this range of temperatures that we investigated was roughly linear. And so as you increase temperature, so if you increase the temperature 40 degrees from room temperature, you see about a 25% decrease. As you increase temperature, you get a decrease in the strength. Conversely, if you cool the material down from room temperature, 40 degrees Fahrenheit, you get a 25% increase in strength or stiffness. And so that just has to do with the behavior of polymers. And like I said, in this particular range, because we're to the left side of the transition glass temperature, we're seeing a roughly linear slope.
Okay.
I guess you told me I could show more slides. I could be doing a better job of showing more slides here. So this is going back to that same idea. So as you increase the temperature, you have that 25% decrease. As you decrease the temperature, you have a 25% increase. And this plot is just showing you some statistical analysis to show you that in this confidence interval where we'd expect the mean, it's not flat. So we do know that there is a slope. What that slope is, obviously there's some uncertainty, but it's about in the ratios that Carolyn mentioned.
Okay. We've got a few questions on cost. I'm going to pick up two of those, and then I'm going to go ahead and transfer it over to Jamal. The first question was, can you address the cost of reinforcing fibers used in this material compared to alternate materials?
So I guess I'm trying to understand exactly the question here. So in this case, we don't add any fiber. So it comes, polymer concrete comes in these pre-bagged materials with the binder and the accelerator and the initiator. And so there's not a need to adjust those fiber dosages. But I can just speak to generally the cost of this so that people have sort of a benchmark for it. And this is information that I talked with the folks at QuickBond before this call, before this webinar, to just ask them some of this information, because I figured that folks might be interested in what the furnished and installed price might be for this. And so that's my disclaimer. This isn't my data. This is what I was told by the folks at QuickBond. and that's the furnished and installed cost for this would be, so the installation cost is very similar for this and for polyester polymer concrete. So that's what folks are maybe used to, and the installation is identical. And so the cost for installation is also identical. What's a little bit different is the material costs. And so HCSC has about a 25% increase, 25% higher material cost. And so for the furnished and installed cost, it's about $170, $180 per cubic foot. And so that's just some general pricing information to give you a sense for how that compares to other alternatives.
Okay, that kind of gets the next question about what was the cost per cubic yard. So I guess you got to multiply it by 27.
It's a difficult question, just because it obviously the material cost is higher than polyester polymer concrete or a conventional concrete. In terms of the material costs and UHPC, again, the material cost of UHPC depends based on whether it's going to be a proprietary or non-proprietary, and it really comes down to how much it costs to place it and what work needs to be done after it's cast. And so I think there's a lot of variables there to think about when we're talking about cost of these different materials. And so for the HCSC, I mean, things that would increase the cost that you don't have to deal with, there's not going to be any need to overfill, and so you don't have to come back later and grind it down. But again, the material itself is potentially slightly more expensive. So I think it's an interesting question and one that I don't have the answers to, but there's a lot of pieces to think about.
Okay, that's got most of my questions. There's a couple more that came in once we started question and answers. And I'm going to get Jamal on, and he's going to go ahead and ask those. Jamal?
Thank you, Paul. A couple of questions came in during the presentation. The first one is the effect of vibrations on the capacity, on the bond capacity between the material and the concrete.
Gotcha, and thank you. Yes, and Carolyn did a tremendous amount of work and a fantastic job. So I think that thanks go to her for all of her hard work. In terms of vibration, so one of the things that I just mentioned in passing was that the dynamic modulus of this material is quite a bit higher than the static modulus, because with polymers you do have that rate dependence in terms of the properties as well. And so I think in terms of the vibration aspect, I guess I need to read the question maybe again, and I'll try and respond.
Our loading is dynamic. Live load on structures are dynamic, even though we design it as a static. And here the question is the impact of these vibration due to impact of live loads on the structures, especially, for example, when you have the connection between girders at the closure pore, how that the bond will be affected due to vibration.
I think it's an interesting question, and certainly one that we didn't investigate. And so I think it's I think in terms of I can't leave any webinar without saying there needs to be more research, because that's of course every academic's job to say. But I think in this case, there's always some additional things to think about, and I think that's one of those aspects of this material that can be further characterized in terms of that dynamic performance. I think QuickBond has some data on some of that as well, but in terms of some of the testing that could be done, I can see answering questions like that, answering questions about the creep. Those are the types of things I think are some next steps.
Yes.
And so I appreciate the question. Absolutely.
That's reasonable. Another question about the protection. of steel. And here they're asking, does polymer concrete provide similar protection to the steel as conventional concrete?
And that's a really great question, and something that I didn't talk about at all, so I apologize. We didn't do any testing on durability, but the interesting thing about polymer concretes and why they're often used as an overlay is that they're nearly impermeable. And so once you have this polymer in there, it doesn't accept water in the same way that cementitious concrete matrix would. And so you're essentially putting a barrier, a moisture barrier down. And so that's going to prevent, as long as you don't get big cracks, which again, the tensile strength of this stuff would be, it would be hard to do, I guess, unless you have some kind of failure in your cementitious concrete that's adjacent to it. But yes, this stuff is basically impermeable, and so you're not going to see a lot of chloride ingress. You're not going to see a lot of moisture penetration.
And that's correct, because this is dense, very dense concrete.
Yes.
So very dense material. Another question about the cost. They say it's too costly, $3,600 a cubic yard. What are the alternative of comparable performance? Thanks, he said. So again, this is about the cost.
Yeah, no, and I mean, cost is always an issue, and so I think there's different ways to reduce cost, and again, I think making sure that you have the right alternative for the particular project and the scope of the work that you're doing is so important. And so that's why we set out to do this work, is really looking for different alternatives. And so thinking about polymer concretes, thinking about this fiber reinforced polymer concrete especially, I think the place where it's really going to be successful, or where it's going to win out, is if you have the really short closure windows, and when you really need that rapid return. And so for many of these ABC overnight type of work, you could see that would be quite helpful. And if it means you can open the road to traffic sooner, maybe there's a perceived cost savings there that makes it worthwhile. It also, just in terms of the material costs, there's the placed cost, how much it costs to actually install it, that again need to consider as well, and then just trying to minimize the closure joints widths and how much material you need to place in there as well. So so I think there's a lot. Cost is a really complicated issue, and I think without putting pen to paper for a particular job and seeing how things stack up, it's hard to have a full conversation about it, because I think there are going to be some cases where other alternatives make more sense, and I think there's going to be some applications and some projects where this is very competitive.
So I really would thank again our presenters, and thank you very much to our Q&A moderators. Just a couple of quick things, and then I'll end the presentation. We do have our next quarterly research seminar will be on April 26th. It'll be bond behavior of nano-enhanced polymers, concrete for bridge deck overlays. Please put that on your calendars for April 26th. And then coming up on February 15th, we have our next monthly webinar, which will be implementing the new specifications for the National Bridge Inventory. It'll be a presentation by the Idaho Transportation Department to share their planning with us. And lastly, just another reminder that we do have our call for abstracts open for the 2024 World Bridge Engineering Conference, which is scheduled from December 11th through the 13th in Miami. And again, the call for abstracts is currently open. There's a myriad of topics. Please do turn in your abstracts, and please plan on joining us for that Bridge Engineering Conference. Thank you all for your attendance, and the presentation is complete.